Hello and welcome to Unit 4, our final unit for the 4U course, and that's the wave theory of light. And today we want to go through and talk about wave behavior. So what is our goal today? I want you to be able to explain wave behavior with respect to how waves interact with barriers, different mediums, etc., etc. And then we want to translate that and move that into how does it relate to real-world applications. So just a quick review of 3U. What did we do to prepare ourselves for light? Well, we talked about sound. So we talked about how sound waves behave, and we did a whole bunch of stuff. And the relationship or the connection that we drew with sound waves is we talked about how do water waves behave. Because there is a direct correlation here. Waves exhibit the same type of properties, the same nature. So the investigation you did in the 3U course looked at how water waves behaved, then we translated it over to sound waves, and then from there, we're going to move from sound waves into light waves. All right, so some of the things that we talked about with the sound waves, if you recall, just the general structure of the wave, and this is the more useful form that we're going to be kind of following through. And in this particular wave, we have a couple of things that are very important for us this year. We have our crest and our trough. And our trough. That distance from crest to center line, or from center line to trough, that is our amplitude. And from that, the next important thing that you need to bring forward for me is V equals F lambda, or our universal wave equation. That is our universal wave equation. All right. Now I'm going to talk more specifically about the other stuff. And the first component here, the first part of this review, or first part of this lesson is review on that 3U and talking about some of the wave properties that arise. Okay, so moving along then. Starting off with kind of the easier end. Talked about point sources. What is a point source? That would be like placing a speaker in the middle of the room or yourself and having you talk. So with a point source, put it in the middle here. Waves then, if that is a source, waves then emanate in a circular shape outward from the point source. Okay, and it's emanating out in all directions. And that's how we draw it. And what we would do is, or what at least my convention here, so I'll put this off to the side, the convention, we are drawing the crests. All right, so whenever you draw a wave diagram for me, we're going to assume you're drawing the crests, which technically would mean that your troughs are located in between. So we're not going to draw these in. I'm just going to do it on this first diagram. Just when you look back, you can remember exactly what the convention is. Okay, so troughs are going to occur in between the crests, but we don't need to draw those in because it's an assumption. We know it's in there, right in between. Okay, so there is our point source. Moving along, this one became very important for us, and it's going to be extremely important for us as we move into Young's double slit experiment a little bit later on. So talking about 2 point sources. So I'm going to sketch this as best I can. So drawing, again, a single point source. And then placing a second point source in the same vicinity, it then generates its waves. Very similar. All right. And of course, they emanate outward in all directions. So what happens here? All right, I'm going to put a couple more circles in, maybe as best I can. And maybe put another one in like this. And you'll remember, those that use the applet, a distinct pattern arose from that. And that pattern was a series of black lines. Okay, a series of black lines. And those black lines were occurring wherever crests and troughs were interacting. Wherever crests and troughs were interacting. So what you would have then is anywhere that these two lines are interacting or overlapping, we're going to have constructive interference. So your constructive interference would be occurring here here, here, here. So in anywhere the red and the green lines are overlapping. Wherever the red and green lines are meeting kind of in the middle, so we're not going to be able to do all of them. I'm going to take a couple here. We get a pattern outward, and if you recall from last year, the lines emanated outward. So the next one would have been here and here. If we move over, we're going to have destructive interference in there, destructive interference in this area. So we get these lines of destructive interference. So we're just going to kind of sketch them in. And these are black lines represent regions of destructive interference. Destructive interference. All right. And maybe I'm going to pull up a picture that's a little bit better for those that don't quite remember that. Okay, so this little YouTube video here, I have it playing. I have the website up on my website. But what it shows, it is in 3-space, in 3D, and we have 2 point sources, and you can see these regions of destructive interference. And I'm going to attempt to draw on top here. So it does work. So here are regions of destructive interference. There's no wave pattern occurring in these particular lines. That's because the crests and waves are meeting at those points. And again, in grade 11, we talked about putting the rubber ducky in the tub. Rubber ducky will not be moving or oscillating up and down in those regions of destructive interference. So letting that play out, you can see that it doesn't change. Okay, and those regions remain kind of dark or black areas. So again, these regions right here are your areas of destructive interference. So feel free if you want to pause this and go back and try the other video and see this live without my lines on top. It gives you a feel for what my diagram was supposed to look like. That's this one here. All right, so that is that destructive interference pattern with 2 point sources. Okay, moving along. We now talk about the plane wave. So the plane wave is waves that are straight lines. All right, so again, I'm drawing the crests. So this would be created by, if you had in the pool and you had maybe a pool noodle and you were headed straight and you started bringing it up and down, plane waves then would emanate from it, traveling in a straight line as such. If these plane waves were to meet an object or strike an object, then the angle of incidence would equal that angle of reflection. So I'm going to try to just kind of sketch this out. So here's my blue wave striking the barrier. That angle I'm talking about, this angle right there. So there is your angle theta. So in green, we would find that the wave then would reflect and would look like, do this properly or try to do it as proper as I can. It's going to head in this direction, our plane wave. So it's like bouncing a ball off an angled wall. Okay, so your plane wave will move and remain in this kind of straight format. Okay, so that's what that plane wave is. So they're basically straight waves instead of the curved waves you get from the point source. Single slit, and this is going to be, last year we investigated it and it was very, very important. And there's 2 slits. So we got let's go with a wide slit and a narrow slit. And on top of that, there was 2 conditions within there. So the wide slit, we're going to do a low frequency and a high frequency. We're going to do that for both low freq and high frequency. Each one behaves a little bit different. So there's what our 4 diagram categories are going to be here. So low and a high frequency for the wide and narrow slit. So for the wider slit, I'm going to exaggerate it here. And for the narrow, oh, that's still the wide one, sorry. For the narrow slit near the bottom here, I'm basically going to make it a pinhole. So we can make that comparison above and below. Should actually make it look like there's a hole though. There we go. All right, so low frequency means that the waves are, excuse me, significantly spread out. All right, so I have 3 waves and they are heading toward that slit. In green, I'm going to draw the resulting waves. So we're going to have waves that are the same size as the barrier reflected back. Okay. We are going to have a portion of this wave pass through. When it passes through a slit, the wave will then expand, and it takes on the appearance of a point source. Not quite to the extent. So the edges start to bend around, and then the wave will spread out. Okay? And it spreads out in all directions, just like that. Now the high frequency means that my crests are closer together. All right, same thing, I'll do it in blue. Waves that strike the barrier will reflect back, same as a ball would. Wave that gets through here though, in that high frequency, it also spreads out, but if you recall, high frequency waves for our investigation do not spread out nearly as much as a low frequency. So I'm going to exaggerate it so that this cone is much, much narrower than the low frequency. So I've exaggerated it so you can see that the cone is significantly different between the two. Okay, so low frequency will always spread out more. High frequency doesn't spread out nearly as fast. What happens if we shrink that slit? Okay, so what happens if we make the hole that it's going to pass through a lot smaller? So low frequency, I'm going to try to draw the same sort of spacing for my waves. We still get that reflection back. And now we have this little bitty hole. As that hole gets smaller and smaller, it starts to act more and more like a point source. And if you pass a low frequency through a very small hole, then it starts to act more and more like a point source. I'll just spread them out a little bit more. All right, so low frequency will spread out virtually like a point source. Not quite, but pretty darn close as that hole gets smaller and smaller. High frequency though, high frequency, and exaggerate this a little bit, like this, and then you get your reflection. And the high frequency will spread out, not as much though. It will spread out more than it did above through the wider slit, but the low frequency will still spread out more than the high frequency will. Okay, and we're going to talk about why that is when we talk about the single slit and Young's double slit. Okay, so single slit and double slit as we get a little bit further on. We'll show you the math behind that this year. All right, so that's taken from our grade 11 course. Okay, I'm going to pause it there and we'll pick it up in the next video.